Okay. Well, we gotta go to videos at the end of last semester, but you guys weren't here. A lot of you were. Some of you were. You guys that are freshmen were. I'm gonna do a bunch of videos. So what you'll do is I'll put up a set of videos. You'll write lecture notes. You'll turn them in. Once you turn in from those lecture notes, I'll grade your lecture notes basically. That's what I'm gonna do. It is what it is. We make the best of it as we can. And honestly, I didn't know anything about it. It caught me just as off guard as it did you guys. Let's talk about torque. Some of you may be torqued up over the decision to go virtual with the rest of it and online. You may have heard that term before, but let's think what torque is. Torque, really, you want to think about it, is rotational force. Force is a push or pull. Torque is how much you want to push or pull something to rotate it. Tire irons are really good things thinking of torque. If you're going to use a tire iron, anytime you rotate anything, you're generating a torque. Have a pipe wrench here. Use a pipe wrench, you put it on a nut, and then you torque it around, and that tightens or loosens the pipe wrench. Loosens the nut that you've got, that you're trying to tighten on the pipe. Now, torque depends on a few things. It depends on, of course, the force applied. If I just barely push on it, it's not going to want to rotate it much, of course. If I push on it here, I'm going to get less torque than I push on it here. Because the distance away from it matters. We're going to call that the lever arm, or torque arm, or distance from the point of rotation to where your hit that force is that's making it rotate. Traditionally, it's called a lever arm. And it also depends on the angle between the force and lever arm. Depending on the angle between them. Now, it's going to depend on this way. If this is the lever arm, and this is the force straight, if I do it straight down, you're going to get the most torque that way. If I pull this way, am I getting any torque? Does it want to rotate at all? No, it's not. If I do that way, no rotation. Now if I go this way, up at an angle a little bit, I get some, but it's not doing a lot. If I do straight up, I get the most. Straight down, I get the most rotation. So we want the angle between these to be as close to perpendicular as possible for the most torque. So the relationship is the angle theta to give max torque (90 degrees). Theta to give zero torque is either 0 degrees or 180 degrees. And I should put here 270 degrees as well. What you can say here is perpendicular, here parallel. If the lever arm and the force are parallel, you get no torque. If it's perpendicular between the lever arm and the force on it, you get max torque. Now, so what trig function gives you a relationship where its maximum value is at 90 or 270? Let's do absolute value, not include negative or positive. Just its maximum value is 90 or 270, its minimum value is 0 to 180. Well, since I can't call it anybody, I can pretend, but of course that's the sine function. We know the sine of 0 is 0, the sine of 90 degrees is 1. And of course, the sine of 270 is negative 1. The sine of 180 is 0 as well. So we're going to have a sine function in this formula between them. So what I'm going to say is, and the book does this based on kind of definition, torque is the magnitude of the force, and they use R for the lever arm. The magnitude of that lever arm times the sine of the angle theta. And theta is, of course, the angle between, this is angle between the force vector and the lever arm vector, which they're using as an R vector, like a radial distance away. Now they're using it. Things about torque. It's always based on the pivot point. Or you could call it your point of rotation. That's what's doing the rotating. That's how you measure this R value. So if I do a little picture here, up here, you can think of this as, say, some nut. Here's some wrench over that. And here it is a distance. So we're going to exert a force, say, upward here at 90 degrees. So if that's going on, then this distance here to here, and it's to the center of rotation, so it's the center of that nut. Most of the time it doesn't matter. But if you got if the nut on that you're turning, the bolt is really big, and the head on that nut that bolt's big, and you got a short lever arm, it wouldn't matter. This will be, well, it's from the point here, so it's going to go out. So this is your R vector, and this is your F vector, like that. And of course, in this case, it's theta. Let me call this theta right here. It's the angle between the two. Now, I could base it off of here if you wanted and go all the way around. Of course, that would be 270 degrees. But as long as I'm just looking at this relation between the two, so it's on this side I'm pushing, so we'll just use it off of that x-axis there. And honestly, it's pretty straightforward. To do an example with this, you just find each one of those and plug it in. Use each one of those and plug it in. Now, there's some vector stuff the book doesn't go into. I'm not going to get into it. There's a little bit more to it. This is actually a cross product, which I don't think we've talked about much. We'll get that a little bit more next semester. What I do want to talk about, I want to say a couple things here. I think you can see this. Let me make sure. Okay. There. A couple things. Torques are additive. Okay. So in this situation here, say I've got, rather than a nut now, this is teeth on a bicycle. And coming out from there, I've got pedals on both sides, right? You've got pedals on both sides. So if I'm cranking that pedal, I'm going to put a force here on one. So you know on your bicycle, you push down on one, so you push it back, and you push it down on this, and if you're strapped on it, you kind of pull up on the other one if you got any straps. Maybe you had Pelotons or anything like that before. So if you're down on this one, and then you'll basically go up on that one. And so the net effect is the total torque. We'll call this torque 1 and torque 2. Total torque, we just sum them up. Now, the direction of rotation matters. If they were in the opposite direction, if they didn't both make them want to rotate the same direction, if I put this on the other side, then I'd have to subtract that. And that's where 90 versus 270 would come to, one would be positive and one would be negative. So just be consistent on that when you're doing that sort of work. Gravitational torque. What I want to say, to balance objects must take into account gravitational torque. Gravitational torque is interesting. You might have saw the trick where you put somebody against the wall, you put a $20 on the floor, and you say, all right, without bending your knees and keeping your butt and everything against the wall, bend down and get the $20. Well, people can't do it. Why? Unless you're really, get your thighs or thunder thighs or whatever. But you can't do it because what happens is your center of gravity, which is your center of mass, that's where your body pulls on you. Your body pulls on you there. Gravity pulls on you there. So as it leans out over your supports, when your center of mass is not over your feet, I guess you had duck feet or something, you could do it. But if it's outside that end of your shoes, into your feet, you're going to have a torque to fall over. Gravity's torquing you over. You see sometimes pictures of people doing this in football and stuff, or in different sports and things, gymnastics, bending and everything. For them to stay above, they've still got to keep. Now you do it for a little bit of time like this, you fall because you can turn the other way. But if they're static, you can't just lean like this and not fall down, because I don't want to fall down. I keep on going too much. Okay? What's happening, my center of gravity is not in line with my feet. And if it's off to the side, there's a net torque. One way to think of it, I have a little system here. So you would think it would be in the middle. Well, the middle is like right here. Well, gravity is making it rotate, right? Because normally if these weren't on here, I could do it at the center of mass and it would balance, right? But why does it not want to balance? If I hold it here, it rotates. Gravity's rotating. If I hold it here, gravity's rotating. If I hold it here, you know what's going to happen. It's rotating, right? Why does it rotate? Well, gravity is exerting that force. Where at? At the center of mass. And that's key to know. It's key to know. Gravity exerts a force down at the center of mass of the object. Gravity tries to create a torque at that center of mass point. So, of course, to counterbalance it, if I put this on the end, I have to hold it at its center of mass. Ooh, I'm getting close. Right about there, right? Right about there. It's off to that side. Now you say, well, what if I do it here? What have I got to do? Because it's going to want to rotate. Because the center of mass is like right there and it's trying to rotate. Well, I have to exert a force upward. So this is the pivot point that actually is exerting a force upward. And I have to create a torque in the opposite direction, this force upward here over this distance. And if I'm out here further, I got more lever arms with less force, so you can actually feel it. That's a little bit heavier. I got to push up. It feels heavier there than out here. Why is that? Because I don't have to exert as much force to keep it balanced. Here, I got to exert more force because my lever arm's shorter. I got less torque upward to counteract gravitational torque downward. Got to counteract that gravitational torque downward. And that's a good introduction of what we're going to do next, which is static equilibrium. And that's on section 12.8. So I'm going to erase this. Adjust it back a little ways. All right. So let's look at this static equilibrium problem, because gravity's pulling down the center of mass. We got to pull down here. I'll put these close together. Because that's about close they'll go. So we'll say that's just one mass pulling down. So got a torque force that's equal to the weight of this. I've got gravity pulls on the center of mass. So we can assume all the mass of this rod is acting at one point. So let's see if we can figure out how to calculate how much force I have to push up, because I have to generate a corresponding torque in the opposite direction to keep everything in equilibrium. So everything's balanced. Okay. So for static equilibrium, and this is 12.8, static equilibrium. Now, static equilibrium is not moving and everything's balanced. There's stuff called dynamic equilibrium. That's when it's moving, but it's not accelerating. It's not changing its velocity. Basically, in static equilibrium, there's actually, when I taught mechanical engineering in Charlotte, there's a whole course that's really the first real introductory mechanical engineering course that students take, called statics. And you do this for a whole semester. You basically do this section for one semester. You get really deep into it and really get all the details. And you can do these, you do pliers. Pliers are really linkages and stuff like that. Let's look at what static equilibrium. Now, for things being static equilibrium, to be in static equilibrium, you've got to have two things happen. You must have the sum of the forces equal to what? Sum of the forces equal to what? Go ahead and type it on your chat line and let me know. Oh, we're not synchronous. This is a video. So I'm going to say it's 0. And that makes sense. If some of the forces are 0, it's not going to accelerate. It's already static equilibrium. So, it's not moving. And what about the torque, though? Now we got to deal with the rotational force, because things want to rotate. Well, then the sum of the torques has to equal 0 as well. Some of the torques have to equal 0 as well. Now, this must be true. Now, what I'll say is, for some of the forces, that means the sum of the forces in x equals 0, some of the forces in y equals 0, and some of the forces in z equals 0. And for torques, we normally use clockwise and counterclockwise. Now, I know that's old school. And you guys say, what's clockwise? I don't see an analog clock. Analog clock, right? Clockwise. Clockwise means it goes this way. I sound like a Jar Jar Binks, right? This way. But it goes, so it would go down from about first quadrant to fourth quadrant. If it swings that way. If it goes from first quadrant to second quadrant, from the unit circle stuff, that's counterclockwise, the opposite way. Not this way, the other way. Ooh. So that's clockwise. You see that going around. Tink, 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 tink. All that clockwise, right? That's clockwise. Counterclockwise is the other way. So with torques, what you have to say is that the sum of all the clockwise torques has to equal the sum of all the counterclockwise torques. Or another way you could write this is for equaling 0, the sum of the clockwise torques minus the sum of the counterclockwise torques, that has to equal 0. That's how you write it. Okay? And that's how you write it. So let's look at some examples. Now the book does some examples. I'm going to do just a simple one first. Then we'll look at example 1214 in the book. That's got a lot into it. I just want a simple one first. So I'll let you write it down. Let you have the time. Of course, you can stop the video and write it down, right? So I'll go ahead and erase this. So we know we've got to have some of the forces equaling 0 and some of the torques equaling 0. Let's assume this is one force. And I'm going to make up data for this because I didn't measure it beforehand, but we'll get close enough. All right, so this thing is about 30 inches long. Okay, it's not a meter long, say 30 inches long. All right, so let's take this. We'll say it's 30 inches, so we'll call that we'll say 0.90 meters long. 0.90 meters long. Actually, that would be, say, 0.85 meters long. All right? And I'm going to hold it at a point right here. That's going to be our little pivot point. And I'm going to have a mass, I'm going to have a force down right here. And we'll say this force is equal to about a Newton. That's about let's say that force is equal to, we'll say 10 newtons. 10 newtons. We'll do everything in 2 sig figs. We'll take this thing, its center of gravity is going to be in the middle. It's going to be in the middle. So it's going to be right here. Now, it's going to have coming down on it, let's say, I don't know, let's say 40 newtons. We'll say 40 newtons. And what I had to do, because that's overcoming it, I got to exert a force up here. So I'm going to exert a force right here up, and that we don't know. But let's get some distances now. That's 85. We know we're going to put this at 0.30. So that's 0.85. 85 meters is totally half of that, because we assume it was in the middle. We can make that assumption. That'd be 0.425. Let's round it out to 0.43. So this is equal to 0.43 meters. So if that's 0.30, that distance there becomes 0.13 meters. Because it's just the distance from the center of it. We're assuming center mass for this rod evenly distributed like the center. Now let's say this distance over here, that looks like it's how far? I'm going to do the arrow the other way since that's from the pivot point. We'll say that's 13. We'll say it's 25 meters. We'll say it's 25. I'm doing everything in meters. Probably should have done it in centimeters. I'm sorry. Let's do all this in 0.85 meters. No, it's 0.25 meters. It's 0.25 meters. Okay. All right. Let's find the force. So that's this problem here. I'm holding it here. It's wanting the torque, and I'm exerting force up with my finger to generate a torque to stop it from rotating. So let's do this problem. Okay. Sum of the forces equals 0. Got to take into account the vector nature. Now, all these forces are either up or down, right? They're either up or down like that. So what I'm going to do is, we'll assume everything's in y. So we'll make this the y direction. We'll make this the x direction. Okay. So if we do that, so that's going down, that's 10 newtons. So that's 10 newtons down. That's going to be minus 10 newtons. And we got 40 newtons down right here, minus 40 newtons. And right here, we got some force up. So that's going to be positive. Some force up. Okay. And that's total of all this. Some of the forces have to equal 0 is 0. Alright. And some of the torques equaling 0. And let's see. So there we do it on each side. There we do it on each side. So we do it on each side here. Let's look at, so we're going to do the torque on this side, and that would be torques clockwise minus torques counterclockwise, and that has to equal 0. Okay, so let's just do this here. So this would be the counterclockwise torques. It's 10 down, and okay, we were saying that was out 30, so I need to move it on the end. I put it on the end because I just want to make it match reality as best I can. So, pivot point, so 0.30 meters. Force is 10 newtons. Make that minus. And over here, we got 40 newtons. Coming down, so this is clockwise. So that's clockwise, so we got 40 newtons times 0.13 meters. And now we gotta look over here at total distance, but that's going up, so that's counterclockwise as well, so that's going to be a minus. We don't know that force. And we're going to say that distance is 0.13 plus 0.25, so it's 0.38 meters. And so that equals 0. So let's solve this one for force. I know. Let's just do this one. That's a force up. Okay, so 10 times that, 0.3. This is minus 30 Newton meters. 3.0 Newton meters. 40 times 0.13 is 5.2 Newton meters. And there's no unit for torque, it's just Newton meters. And that's going to be positive. So that's minus force up. That's 0.38 meters. Bring this to the other side. And we take this to the other side, 5.2 minus 3.0, that's 2.2, so it's negative 2.2 Newton meters equals minus F up 0.38 meters. Well, the negatives become positive, but they cancel, so we then divide both sides by 0.38 meters, 0.38 meters, so F up is going to be what? And 0.38 into 2.2 is, that's going to be awful small. And what do we have? So, let's see, that's 4 to 22. That goes about 5.5. So 5 times that would be 1.9. Actually, 5.5 is pretty close. Let's say 5.5 newtons. All right, very good. So that's what some of the torques said. Let's look at some of the forces. Ooh, if I put 5.5 right here, does that equal 0? Heck darn no. So what did we do? classic mistake. Not that I did it on purpose. Classic mistake. Most people look at it like this. Are there any other forces in this situation we did not take into account? Are there any other forces in this situation we did not take into account? Yes. What force is that? Where are their forces at? There's a force right there at that pivot point. I mentioned it earlier. The force at that pivot point. So some of you are going, Knight, you're shady, you're messing up, you forgot about it. Good stuff. Those are whatever. Pay attention. I gave you a hint on that earlier. There's actually a force right here going up that we don't know as well. Force of the pivot. So in reality, the reason I didn't solve this to begin with, there's actually two forces here. We had two equations and two unknowns. That's why you gotta solve for both of them. You gotta solve for both. Now we know the pivot point. We know the pivot point force now out here. So we can now say that minus 10 newtons minus 40 newtons plus the force up 5.5 newtons plus the force of the pivot equals 0. We gotta include that. Don't you forget it. That's an old SpongeBob reference for some of you. So now we can solve this. We only have one unknown. So minus 10 is minus 40 is minus 50. When the other side that becomes 50, we'll just do this is minus 10, minus 40 is minus 50. Minus 50 plus 5.5 is 45.5 negative. Bring the other side, make it positive, because that is an upward force, so that's right. So we get 44.5 newtons. And that makes sense because you don't have to exert a lot of torque, but I've got a lot of force there on my finger that hold it. The finger holds it, your pivot point also is pushing up because it wants to collapse down, so it has to push up with a normal force there. And that lets you find the two unknown forces. Okay? That lets you find the two unknown forces. Use torque and force. This problem is actually very simple, very similar to the one for lifting weights. They phrase it a little differently, but it's a pretty similar problem. They got a pivot point at the end. Now, this is what's known as a first-class lever. There's second and third-class levers where they're like a wheelbarrow is a type of lever, and then this lifting weights, your joint, like an elbow joint, is a type of lever as well. But they don't get into. You may have heard that in some of the other classes. But from our perspective, we just care some of the forces equal 0, some of the torques equal 0. So example 12.13, real similar problem. 12.14, walking the plank. 2 forces up, 3 forces down. We had 2 forces down and 2 forces up. Same problem. You do it the exact same way. I would definitely recommend example 12.13, 12.14, put in your notes. Will there be one like this on the final? I can guarantee you'll have a problem like in static equilibrium on your final. Okay? Guaranteed it. Because with static equilibrium, I'm also doing torques and static equilibrium. Okay? Any questions? Alright, so one thing I want to talk about regarding balance, and I talked about this earlier, and the book talks about it at the very end. For balance to occur, center of mass must be over a support or sum of the forces have to equal 0, and the sum of the torques equals 0. I can lean over like this, where I would normally fall down, if I've got a string pulling up on me another spot, like a puppet, that keeps it from falling down. So if you have additional supports at work, but if you have a non-zero torque on something, it will rotate over and fall down. The leaning tower, why does the leaning tower of pizza not fall down? Because it's got pepperoni on it, right? No, I'm joking. Why is it not leaning tower of Pisa? Why has it fell down yet? Because, the base was really soft, and as it did, it started doing it. It hasn't fell down yet because the center of mass for that is steel, because they built it wide at the base, and it got short, a little bit, not a lot, but then it got thinner at the top. As long as that center of mass stays over support, it won't fall. Now, what they could do, and I don't know, they could actually have additional support there, not just based on weight, to hold it in, to keep it from falling anymore. And I'm pretty sure they've done that. But those additional supports have to counteract, because it's falling over, it's trying to generate a torque. That's creates a torque. Yes, there's a counter torque the other way. If you drive pilings into the ground and anchor there, and they basically create a torque the other way, just with their stiffness, you can keep it standing up. I'm pretty sure they've done something like that. That's actually a similar problem, not exactly the same, but similar to the ladder. The ladder slip problem is a little more than what I want to go into, so don't have to worry about one like that. But just understand stability. For balance to occur, stability, some of the forces have to equal 0. Now, they go into this, they go into angular momentum. Gosh, I wish I had time to go over angular momentum. I'll just be honest, I won't hit angular momentum in 301. Basically, it's just saying when things rotate, they have momentum as well, and that they want to keep rotating. They want to keep rotating. And momentum is inertia and motion in a straight line. Angular momentum is inertia, a rotation in rotation. Things want to keep rotating. Okay? Things want to keep rotating. That's angular momentum. For section 1211, I'm just going to say, know what it is. Rotational inertia, and know examples. What are some examples? Well, something's rotating when it keeps on rotating. If you have an ice skater and they hold out their arms, there's a lot of mass away from the center of rotation. It doesn't want to rotate. Okay? Doesn't want to rotate. It takes torque to do that. There's a lot of torque to make it rotate. How does an ice skater go faster when they're spinning? They bring their mass in. What do? They rotate faster. Because that momentum is conserved, just like in linear momentum. So there's less torque needed to rotate that slow, and so it has to rotate faster when the mass is real close. Some examples to show. Make sure you look that up as well. But I'm not going to give you anything on the final as you calculating your momentum, but I do want you to know what it is. Make sure you can see that. Now you can see that. Now you can see it. So know what it is. It's rotational inertia. Know what that means. And be able to discuss some examples that demonstrate rotational inertia. A flywheel. You know what that is? Once it keeps on going, it's a heavy mass that once it spins, it doesn't want to stop. And it's pretty useful. Your car tires, you get a tire going, it just wants to keep on rotating. It wants to keep rotating. You've got a heavy tire versus a light tire. Heavy tires, once they keep going, it's hard to stop. Brakes heat up because they're trying to pull the energy out of these rotating tires. Rotating wheels with them. And the heavier those are, the more angular momentum they got. And that energy in that rotation has to go somewhere. It goes into heating up the brakes, that thermal energy. Also, if you have lighter wheels, you can stop faster. Why? Because they've got less angular momentum, less rotational inertia. They're less mass. If they're rotating fast, it's easier to slow them down because they've got just the mass itself is less. Smaller tires have less rotational inertia. Why? Because it takes less torque to slow them down. And torque is lever arm of the thumb. So bigger lever arm, more the torque. So you have to create an opposite torque the other way to slow it down. That's going to take more energy to do. So a smaller tire will stop faster as well. So if you want your car to stop faster, you put giant wheels on it. You might get more friction, but the rotational inertia is going to be hard to overcome. That's why those sports cars like that have to have really big brake pads to take the energy of that so you don't burn up a regular pad. It has to take all the energy and it keeps it from, it allows it to have the capability to stop at that larger one quick. That's why you have to have bigger it's pads and the brake pad is it too. I can't remember. Alright. 5 more examples. I'll say big wheels. Some of you have a big wheel, like as you maybe have one as a little kid. Once that thing goes, it keeps on going. If you have a trike, a little tricycle, once you stop pedaling, it slows down pretty quick. You pedal a big wheel, it gets going. That big wheel's got more mass, and once it gets going, it keeps on going. And you'll coast further. More rotational inertia, greater angular momentum. Alright, hope that made a little bit of sense. That's all we're going to do in chapter 12. Next lecture will be on 13. That's gravitation, so be ready. Get notes, get it in. Thanks.